Hello, I am Seema and welcome to part 19 of the chapter Hydrocarbons. We were doing the isomerism in alkenes and I told you that there are two kinds of isomers, that is the structural isomers and geometrical isomers. In the previous video I told you about the geometrical isomers that alkenes show cis-trans isomerism. When two similar groups fall on one side of the double bond, we call it a the cis form, and if they fall on the opposite sides, we call it the trans form. So now in this video, I'm going to be solving three problems based on geometrical isomerism. Two of these are your solved examples of your textbook, and one is your textbook exercise question. So not wasting any time, let us straight away start with the questions. The first question is question 13.10 and it reads, you to draw the cis and trans isomers of the following compounds. Also write their IUPAC names. So the two compounds that are given to us are CHCl, double bond CHCl. Whenever you have to write the cis-trans isomers for any compound, you have to find the two carbons that are bound together by the double bond. And then all the species that are connected to those carbons, you have to check those. Each one will have two species attached, or two groups or two atoms attached to it. Then we'll write them and see if they are similar or different and if we can have the cis-trans isomerism. Okay? She was very interested in coming to this room, so I let her be in the video. She is here as a student. So she's going to study about cis-trans isomerism, isn't it, Peachy? Okay, wait here. Let's solve the questions. So, the first one is CHCl, CHCl. So, let's write the carbons have the double bonds with them. Okay, carbon, carbon double bond. With this carbon, you have one hydrogen and the other one is a chlorine. And with this also, you have a hydrogen and a chlorine. So this becomes clear. You can easily write the cis and trans. This is the cis isomer because both the chlorines are falling on one side and both the hydrogens are falling on the other side. So this is, you to also write the IUPAC names. So what will be the IUPAC name of this compound? This is ethene and it has got two chloro groups attached to it, to the first carbon and the second carbon. And it is the cis isomer. So the name of this compound would be cis 1,2-dichloroethene is the name of this compound. Cis 1,2-dichloroethene. Let us draw the trans isomer now. The same two carbons have got a double bond, one hydrogen, a chlorine, and on this side you will have chlorine and hydrogen. So the hydrogens are falling on the opposite sides and the chlorine are also falling on the opposite sides. Now the name of this, the IUPAC name will still be 1,2-dichloroethene, but this is now the trans isomer. So we'll write trans 1,2-dichloroethene. Right? So actually, you should be writing it in one line here. It is continuous. Just like this, this will be trans 1,2-dichloroethene. So these are the names, IUPAC names and the cis-trans isomers of the first compound. Let's come to the second compound now. It is C2H5, CCH3, double bond, CCH3, C2H5. So which are the two carbons? Do you see here? This carbon and this carbon are actually attached by a double bond. Why? Why is this CH3 not with the double bond? Because any carbon that is attached to another carbon by a double bond should form only two other bonds, because carbon can form only 4 bonds. So if this carbon has 3 hydrogens, it cannot form a double bond. It is actually a branch of this carbon. I'll just show you the structure. C and C have a double bond. Okay, this carbon and this carbon. To this carbon, there is one group which is CH3 and the other group that is attached is C2H5. On the other side also you have the C and CH3 and C2H5. Right? So this is the cis isomer. Why? Because both the methyl groups are on one side and both the ethyl groups are on the other side. So this is the cis isomer. And for the trans isomer, you will have CH3, C, C2, H5, double bond, C. Here you will have C2H5 on this side and CH3 on this side. So this is the trans isomer. Right? But what about writing its IUPAC name now? In order to write down the IUPAC name, the longest chain rule tells us that you have to start with, you have to look for the longest chain. C2H5 are 2 carbons and C2H5 again here are 2 carbons. And the methyls are single carbons. So we'll take the longest chain as 2, 3, 4, 5, 6. So these are 6 carbons. It's a chain of 6 carbons. And the methyl groups are on the second, that is the third and the fourth carbon. Right? So you write 3, 4, dimethyl. The D should be a capital here because we are starting the name. 3, 4, dimethyl. For the cis and trans, we do not write a capital. Right? Yeah. 3, 4, dimethyl, hex, and where is the ene? Hex is on the third carbon. Even if I count from this direction, 2 carbons, third carbon. The ene or the double bond is on the third carbon. So you write, it is 3, 4 dimethyl, hex, 3, ene is the name of the compound. And what will be the name of this compound then? It is just trans. The name is the same. Now the chain will be counted as 2 carbons, 3, 4, 5, 6. These 2 methyl groups are the branches. Whatever be the direction, you are still going to look for the longest chain. In cis-trans isomerism, the IUPAC name as such does not change except for writing down which isomer is it. So this would be trans 3, 4. There should be a hyphen between these. Dimethyl, hex, 3, ene will be the name of this compound. So this was question 3.10. Give me a moment to write down the next question now. Now this is the next question, the solved example. Question 13.11. It says, which of the following compounds will show cis-trans isomerism? So we have to tell which of these compounds will show cis-trans isomerism. You know, to do that, again, if we draw the structure, it will become very clear to us. And I'm going to draw the structure on purpose. There is a shortcut also, which as I solve, you will understand how it is done. So let's draw the structure first. This is C, and the double bond is between these 2 carbons. So C, double bond, I'm doing the first one. C, double bond, C. Okay, this has H attached to it and the other group is C2H5. This carbon has 2 methyl groups attached to it. Tell me, can you draw the cis-trans isomerism for this compound? If you draw the structure, what do you realize? Even if I moved one of these, the 2 methyl groups are the same. So whatever, even if I switch these, let me try and do it. I have CH3, C, double bond C, CH3, and here I'm switching C2H5 and H. The 2 compounds are the same, they are identical. The only thing is that I'm looking at it from the other side. Instead of looking at it from this side, now I'm looking at it from that side. But on both sides of the double bond, you still have C2H5 and CH3 and H and CH3. So what's the difference? Even if I switched it, I still have C2H5 and CH3 and H and CH3. They are identical. So the first compound, you cannot have cis-trans isomerism for the first compound. So what was the shortcut? Sorry about that. So what was the shortcut? The shortcut is that whenever you see that there is an identical group attached to one of the carbons is bound by a double bond, then one of these two carbons which have the double bond, if any one of them has identical groups attached to it, like here you have two CH3 groups, that compound will not show cis-trans isomerism because switching does not help. So that's the shortcut that you would use. And just to confirm, you may draw the structures and make sure that you're right about it. You'll always be right. Similarly, the second compound, if you really look at it, the moment you look at it, you can tell this is not going to show cis-trans isomerism. Why? Because the two carbons are attached to two hydrogens on one side and two bromines on the other side. When you have identical groups, you cannot have cis-trans isomerism. So let's draw the second structure here. C, H, H, double bond, C, Br, Br. When they are identical, even if I switch one of these, you will still have hydrogen and bromine on the other side and hydrogen and bromine on one side and hydrogen and bromine on the other side. They are still identical. So you will not, this compound will also not show cis-trans isomerism, right? So let us come to the third compound now. The third compound is, these are the two. The hydrogen, you can tell, hydrogen forms only one bond, so obviously the hydrogen is attached to this carbon. So the double bond is between this carbon and this carbon. So let us draw the two carbons which have the double bond, C, C. Now, to this carbon you have a hydrogen and you have C6H5, right? And to this carbon you have hydrogen and CH3. So what do we see? We see that C6H5, CH3, they are different groups, but hydrogens are the same in the two carbons. And if the two hydrogens in this case are falling on the opposite side, so this is the trans isomer, and it is possible for me to have an isomer with both the hydrogens on the same side. So that would look like C, double bond C, a hydrogen here and a hydrogen here, C6H5 on this side, and CH3 on this side. So this is the cis form, where both the hydrogens are falling on the same side of the double bond. So this third compound, yes, it will show cis-trans isomerism. Come to the fourth compound now. CH3CH double bond CCl CH3. These are the two carbons which have the double bond, so let's make the structure for compound number 4. The two carbons which have the double bond are here. To the first carbon you have a hydrogen and you have a methyl group attached to it. To the second carbon you have a chlorine and a methyl group attached to it. So the two groups, methyl groups, are similar groups and they are falling on the same side. Therefore this is a cis isomer, and I can reverse one side. So I'll have CH3 double bond C, and I'll have CH3 on this side and Cl on this side. So here both the CH3s are falling on opposite sides of the double bond. So this is the trans isomer. Okay, so yes, this fourth compound will also show cis-trans isomerism, right? So these were the two solved examples, and now give me a moment to write down the exercise question. Let us now do the exercise question, NCERT textbook exercise question 13.9. The question is, you have to draw the cis-trans structures of hex-2-ene and which isomer will have higher boiling point and why. Let us draw the structure first and then we talk about the boiling point. Hex-2-ene, it means there are 6 carbons, and the double bond is between the second and the third carbon. It is 2-ene. The double bond is on the second carbon. So carbon, double bond, carbon, this is the second carbon. So this would have attached to it would be CH3 and there would be an H here. For hexene, how would you write the molecule for hex-2-ene? You could draw the structures later. It will be CH3, CH, double bond, CH, and CH3, CH2, 1, 2, 3, 4, CH2, CH3, right? So this is the actual structure of hex 2-ene, and if I have to draw the isomers for it, I'll get C, CH3, H, and with this carbon, what are the two groups attached? One is this hydrogen, and the other is this entire group, that is the propyl group. So the propyl group will be C3H. What is the propyl group? Cn, H2n plus 1. So it will be C3H7. So you write here CH and C3H7, right? This is the propyl group. And which isomer is this? This would be the trans isomer. Why? Because the two hydrogens which are similar are falling on the two sides of the double bond. And this is the trans isomer, trans hex 2-ene. Okay? And let's make the cis isomer then. It will be CH3, CH, double bond C, C3, H7 and H. Now the two H are falling on the same side of the double bond. And here the two hydrogens are falling in the opposite sides. So this is the cis isomer. So this is cis hex 2-ene. Now, the question is that which one of these will have a higher boiling point and why? Here, before we come to which one will have higher boiling point or why, there are two things that can happen. If the cis-trans isomerism is present in the solid state, we had studied this in the theory. In the solid state, the melting point is important, like the solid melts into a liquid. And in the gaseous state, in the liquid state, for a liquid, if it is the cis-trans isomerism is there for a liquid, then the boiling point is important. The boiling point of a cis isomer is higher. The boiling point of a cis isomer is higher, and the melting point of a trans isomer is higher. Okay, now this is something conceptual that you should understand. Why is the melting point of the trans isomer higher, and why is the boiling point of a liquid, why is the boiling point of the cis isomer high? When you're talking of a solid, in the case of a solid, a trans compound will be a more symmetrical compound. You see, when you have two bulky groups and two light groups, if the two bulky groups fall on two opposite sides, the weight is kind of balanced. So the packing is better for a trans isomer, right? For a trans isomer, the packing is better. Packing is more efficient. And therefore, in order to separate them or make them slip and slide over each other, turn a solid into a liquid, you will need more energy to undo the packing. But for a cis isomer, two bulky groups are on one side and two light groups are on the other side. The packing is not that even, it is not that efficient. The solid will have weight on one side, the molecules, and lighter part on the other side. So what fixes itself on the, which is the next molecule, how would that fix to it? So it is not a very balanced structure. So the packing in the case of trans isomer is efficient. Therefore, a trans isomer has a higher melting point. But if you have a liquid, we notice that the cis isomer has a higher boiling point for a liquid. And why is this? Is the structure which is balanced not that important here? In this case, as I told you in the previous video, that a cis isomer has more dipole moment. Why? Because methyl group, ethyl group, these propyl groups, these are electron donating. So they push electrons towards the double bond. So the molecule has a net dipole moment. It has a nu which is not equal to 0. But in this case, this will also have a net dipole moment because the two groups are not identical. Yet the dipole moment of this, the trans isomer in this case, will be less, while the dipole moment of the cis isomer will be greater. Dipole moment creates electric poles because if it is pushing electrons, it is pushing the negative charge towards one direction, and both of them are pushing the negative charge to one direction. Then a positive and a negative is created in the molecule. It creates a dipole. That is why we call it the dipole moment. The greater the dipole moment, the more ionic its character is. The more ionic is the character of the compound, and the more ionic it is, the higher will be the boiling point. Right? So, knowing this, what will tell me which isomer of these will have a higher boiling point? The one which has greater dipole moment. And which one has greater dipole moment? The cis isomer always has the greater dipole moment. Why? Because in trans, both of these are pushing electrons towards the center. So they are kind of nullifying each other's effect. Whichever is greater, whichever has a greater tendency to push electrons, that much the difference between the two will be the dipole moment of the molecule. But here, both of them are helping each other. Both of them are pushing electrons towards one direction, thereby increasing the effect of each other. Here, they are cancelling the effect of each other. So that isomer which has a higher dipole moment has a higher boiling point. So the cis isomer will have a higher boiling point. So this was about the geometrical isomerism and cis-trans isomerism and how their properties depend on this kind of isomerism. And with this, I'll wrap up this video, and in the next video we'll take up the next topic, that will be the preparation of alkenes. So if you wish to watch the other videos of this chapter, please click the link above, and if you found the video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.